Hi everyone. We're in chapter 2, the chemistry chapter. And so this is anatomy and physiology. A lot of people think, why do I have to know chemistry for anatomy and physiology? But chemistry is what makes up the human body. It's all the elements that come together to form the molecules, the macromolecules, and eventually the cells and organ systems that make us up. Knowing a little bit about chemistry will help us when we're looking at treating patients, making sure that we're giving the patients the proper medicines or giving them the proper foods. So it's really important to understand chemistry. Chemical reactions are how our body metabolizes. So before we talk about all the molecules that make up the human body, let's talk about what makes up molecules. So matter is anything that occupies space and has mass. What that means is the air you breathe is composed of matter. The chair that you might be sitting in right now is composed of matter. The computer that you're watching this lecture on is composed of matter. And guess what? You are composed of matter. So you matter. I love that. That's one of my little me-isms. Matter can be found in multiple states. Solid. So your table, what I'm knocking on right now, my table, is matter. Liquid, the coffee in my coffee cup, is matter. And gas, the air that I'm breathing right now, is matter. One molecule that is found in all three forms is water. And the fact that it can be seen in all three forms is what makes water so important to life. Water at room temperature is liquid. Water, when it is frozen, is turned into ice. And then water, when it gets very hot, evaporates and turns into a gas. So what makes up matter? Elements. Elements are the simplest forms of matter. Another term for element is an atom. And an atom or an element has a specific number associated to it, so given to it, that helps us to know which atom we're talking about. The number is called the atomic number, and it equals the number of protons that are found in the atom. Atoms also have a mass. They actually have some form of weight. So the mass of an element is the weight of the element, and we can tell the weight of the element by adding up the number of protons and neutrons, because protons and neutrons have a mass. The periodic table is an arrangement of all the elements. And so right here is the periodic table. And so you can see the first element in the periodic table is hydrogen, or H. It's right here. Hold on. And it has an atomic number of 1 and an atomic mass of 1.008. Over here we have carbon. Carbon has an atomic mass of 6 and an atomic number of 6 and an atomic mass of 12.01. So the elements that are important to our body, that make up the majority of our body: carbon, hydrogen, oxygen, nitrogen, phosphorus, and calcium. So, and sulfur, which we typically, sulfur is important. If we don't have sulfur, we can't make up our proteins. So it's not on that list, but it is important, even though it's a very minute amount of our body weight. So here we have all the elements that are really important to the body. These are the elements that make up the majority of our body weight. Sulfur doesn't make up much of our body weight. It's only 0.25, but it's still uber important. Without sulfur, we couldn't make up proteins, and then we wouldn't have our body. We have all these other lesser elements. They're called lesser because they don't make up much of our body weight. But these elements here are very important to maintaining homeostasis. So remember in chapter 1, you learned homeostasis was the ability to maintain your internal environment, different environmental conditions inside the body, like body temperature, blood glucose levels, blood pressure levels. To do that, we have to have all of these elements in our body that help us to maintain homeostasis. So an atom, in a nutshell, has two basic areas. It has an internal area, which we call the nucleus, so it's the center of the atom. And then it has the electron orbitals, or the outer rings of the atom. In the nucleus, we have two types of atomic structures: protons and neutrons. Protons are positively charged. You can think pro-positive, and they have an atomic mass unit. So they have a weight. Neutrons are neutral, neutron, neutral, no charge, and they also have a weight of 1 atomic mass unit. Electrons are found in the orbitals outside of the nucleus, but electrons have such a low mass, it would take thousands of electrons to equal 1 atomic mass unit. So we call electrons, or we state that electrons have no mass. Electrons are negatively charged. There's no neg in electrons, but you can still say electrons, electronegativity. You probably heard that term, so that will help you remember that, okay? And then the outer shell of the electron, the outermost shell of the electron, or of the atom, is called the valence shell. And the valence shell contains the the electrons in the outer shell. These electrons are going to determine if an atom is going to bond to another atom, producing a molecule. So you probably noticed that the weight of an atom, so like hydrogen has 1 proton and has an atomic weight of 1.001. The reason for that is there are isotopes of every single element. An isotope is a variation of the same element. So it has the same number of protons, it is the same element, but it has a different number of neutrons. So this can increase the atomic weight to some extent. The number of electrons stays the same. So again, I'm just showing you this. If you look at hydrogen, hydrogen has an atomic number of 1. It has 1 proton and typically has 0 neutrons, which means its atomic mass is approximately 1. But we state that the atomic mass is 1.008 because we're taking all the different variations of hydrogen and then averaging out the mass. And so all the variations on Earth have an average atomic mass of about 1.008. So let's look at hydrogen. Most often, hydrogen is found as this molecule here, which has 1 proton and 1 electron, no neutrons. But every once in a while, we have hydrogen that gains a neutron. So this is an isotope of hydrogen. So in this case, we have 1 proton, 1 neutron, and 1 electron, and so it has an atomic weight or mass of 2. And then very unlikely, but still occurring, just very seldom, is tritium, which has 1 proton and 2 neutrons. So you've heard of hard or heavy water before. Heavy water is made from the isotope of hydrogen mixing with the oxygen, producing D2O or deuterium water. The radioactive form of hydrogen is tritium, and tritium is a form of hydrogen that's continuously breaking down. It's very unstable. So radioisotopes are unstable isotopes, and so they break down, and when they break down, they give off radiation. All elements have radioisotopes associated with them, and they are continuously breaking down to a more stable atom. And because of this, we have radioisotopes inside of our system, which makes us all slightly radioactive. So radiation isn't all bad. You can think of radiation or radioactivity as, so I should do this, is how we get x-rays, how we do MRIs, magnetic resonance imaging. So radiation isn't always horrible, but high levels of radiation can cause problems. They can cause mutations in cells, they can cause cancers. And so here's just a kind of joke cartoon thing. Judging from your x-rays, I'd say you've been exposed to too much radiation. So they're just continuously giving him x-rays, making him be more exposed to radiation. Oh, but before I go on, radiation also can be used to treat cancer. So you've heard of radiation therapy, where they're targeting those cancer cells to kill the cancer cells, because radiation can kill cells. So if we target those cells that are growing out of control, we can actually kill the cancer. Last thing I'll talk about in this lecture here is the octet rule. So I told you that electrons are found in the outer orbital, and the outermost orbital is known as the valence shell, and valence shells like to have the all of the electron sites filled. So typical valence shells, the first shell of an atom has 2 electrons. The second and third shells of an atom contain 8 electrons, or can contain up to 8 electrons. So in general, we like to have that outer shell full of electrons, and atoms that have the outer shell full of electrons are very stable. If they don't have an outer shell full of electrons, then they are considered unstable, they're unhappy, and they want to bind with something else. And so this is where we get the octet rules. In general, most atoms want to have 8 electrons in their outer shell. There are exceptions. One exception here is hydrogen. Hydrogen has 1 electron. So its outer shell, since it only has 1 orbital, the outer shell has the ability to hold up to 2 electrons. So hydrogen only wants 2 electrons in its outer shell, whereas most of the other ones want 8 electrons. So if you're looking at carbon, it wants to gain 4 electrons. Oxygen wants to gain 2 electrons. That's how it works, okay? I'm going to stop here, and then we'll start talking about ions and ionic compounds in our next video.